Thank you everyone for joining in the week 8 of this problem solving session for the course of Unsaturated Soil Mechanics. And this week, problem solving session is going to be on the analytical methods for transient flow and shear strength of unsaturated soils. This course is basically instructed by Professor T.V. Bharat from IIT Guwahati, and I'm the PMRF TA, Satyam Tiwari from Department of Civil Engineering in Dhanbad. So, as we go into the week 8 of the content, we'll be starting by solving a infiltration problem, which have been discussed in the problem. The infiltration is discussed in the theoretical class, and as we do so, we'll be looking at the problem that it says that an infiltration experiment was conducted in the horizontally sandy soil column shown in figure 9.5. Okay. And the cross-section area, uh, I think I missed the figure. So with the cross-section area of the column is 100 centimeters square. So the column is, let me take the pen. So column is actually horizontal. Okay. And the infiltration is taking place. For that it is subjected to particular head edge at this point, and it says that the cross-section area of the column is 100 centimeters square. The cumulative infiltration volume after 20 minutes of testing was determined to be 200 centimeter cube after 20 minutes. So we need to predict the infiltration rate and cumulative infiltration at 1 hour and at 6 hours. So at 20 minutes, the infiltration volume is provided as 200 centimeter cube. So how do we approach this problem? Is that first we'll determine something that is called uh, that is denoted by S, okay, and it is called absorptivity, okay. So the definition of the absorptivity is that S is equal to the flow which have been taken place, okay, that is going to be per unit area, okay. So that's going to be Q upon the square root of the time. Okay. So the unit of this sorptivity will be centimeter per under root of square under root of seconds. Okay, the time. So how do we approach this problem? Is that first we need to write the value of Q. So it is given the total how much volume is infiltrated. That is 200 centimeter cube. Okay. So the Q will be equal to, if we write for per unit of uh, area, then 200 are divided by the area. The area is given as 100 centimeters square. So that's given here 200 divided by 100. Okay. It will result in, and then we'll put what time we are calculating this absorptivity. That is at 20 minutes. So 20 will be multiplied with 60. So it will result in, if we calculate, that's going to be 200 divided by 100 and divided by the square root of 20 into 60. It will result in 0.0577. So we can write 0.058 as absorptivity. And the concept is that the absorptivity will remain same for every time interval and the whatever the infiltration is there. Okay. So based on this concept that the S value is going to remain the same, that will be 0.058, we can calculate the infiltration, that is the value of capital Q at each particular time stamps. Okay, so it is asked to predict the infiltration rate at 1 hour and 6 hours, then to predict the cumulative infiltration, right? So first we'll do it for 1 hour. Okay, so how we do it for 1 hour is that we write the same equation in different form. That's going to be Q is equal to S square root of T. The value of S we have calculated as 0.058 centimeter per square root of second. And then the time is 1 hour. So 1 hour is equivalent to 1 into 60 into 60. That's going to be 3600 seconds, right? So we'll take 3600 seconds here, and when we'll calculate it, then we'll get the infiltration rate that is equal to the infiltration that is equal to Q is equal to be 3.48 centimeter. So if we determine the cumulative infiltration, that then we'll have to multiply it with the. If we determine the volume of the infiltration, then it will be multiplied with the area. Okay. So this much infiltration have happened in 1 hour. Similarly, for 6 hours, we can calculate the same quantity. The S will remain the same as we have assumed, and the value of the T will be equal to this time it will be equal to 6 into 60 into 60. So it will be multiplied by 6 again, right? So it will become 21600. Right? So we have put the value of time as 21600. So it will result if we calculate 0.058 multiply the square root of 21600. So it will be 8.52 centimeters, right? So these two quantities we have determined, and now we need to determine the rate of infiltration, that is small q will be equal to dq upon dt. So from this expression, if we take the first order derivative of capital Q, it will be S is a constant, so S will remain there. And the square root of T, the derivative of square root of T will be equal to D upon dt. Square root of T will be equal to 1 by 2 square root T at the denominator, right? So it will be S upon 2 square root of T. So at place of S, we'll write 0.058 centimeter, and 2 times square root of T will be this much centimeter per square root second, the unit of capital Q. So this will result in, let's calculate, the value of S is 0.058, okay, and it will be divided by 2 times of square root of T. T is for 1 hour is 3600 seconds, okay, and so that will be equal to 4.833 to 10 to the power minus 4 centimeter per second. Okay, so it's actually equal to 0.00048 centimeter per second. If we convert it to centimeter per hour, then it will be 1.74 centimeter per hour. Okay, so we just need to multiply this with 16 to 60. So it will be the same 1.74. The similar way, we can do the same exercise for 6 hours. Okay, we can determine that Q is equal to S upon 2 square root of T, and it will be equal to 0.058 upon 2 times square root of 21600. So it will result in 0.00020, and then we'll get a value of 0.71 centimeter per hour, right? So in this way, you can calculate that how much infiltration has occurred, and the rate of infiltration also. Okay. So please take your time in understanding this problem, and do let me know if there's any issues with that. So with this, we move on to the theoretical concept which we have understood. The first one is solve the transient power flow problem. We use the Boltzmann transformation, and in this transformation, as we have studied, that Bruce and Fuller provided this equation for the diffusivity d theta x is equal to minus 1 by 2 d del lambda upon d lambda upon d theta and integration of lambda x. Lambda is defined as x upon 100 t fine. So, so lambda is defined like this, right? So, if we plot the volumetric water content theta versus x upon 2t, that is lambda. So, we'll get a plot like this, okay? And in this plot, if you'll see, the slope is equal to minus yeah, because its gradient is downward, so it will be negative d theta upon d lambda. Right? So that value can be put here. So based on this value, we can determine this was d lambda upon d theta. Okay, and the integration of lambda x from theta initial to theta initial to theta x is nothing but the area, right? And so these are the concepts we have studied for the horizontal flow problem. We have several boundary conditions. We have several initial conditions. That at this point, theta is always at saturation, right? And this point is really far, like that. So at this point, the rate of d theta upon dx that's going to be zero. And we can also say that at any theta x greater than zero and t is equal to zero, theta initial is theta naught at that point. So, for solving this diffusivity equation, mm, uh, some analytical methods are there. The first one is the explicit finite element scheme, in which we make use of the Fourier series, and based on that, we convert this problem into a finite difference problem. Okay, so in the finite difference method, we can solve it using you can derive this expression, and you can solve using this. So that is the volumetric water content theta at a particular I value. Okay, I is equal to 1, 2, 3, 4 at this point. That is the iteration at a particular iteration for which horizontal grid, that is the n plus 1th grid. Let's say this one is n and this plus is n plus 1. So for n plus 1th grid, it will be equal to theta I at nth grid plus diffusivity into delta t upon delta x square theta I plus 1 at the nth grid minus 2 times theta I to the power nth grid plus theta I minus 1 to the power n, right? So using this equation, we can solve the diffusivity equation, right? So several other terms are also defined, and we will solve one problem based on the expression which we have defined. Okay, so the problem says that the first two columns that as given in the table 11.2 here, the first two columns which are x and okay, so the first two columns which are x and theta I. Okay, I need one pen. X and theta I, they shows the results from the horizontal infiltration test conducted like in this experiment conducted for a sandy loam soil. Water content measurement were obtained after t is equal to 1500 minutes for several segments of soil column located at distance x from a influent boundary. Okay, so at several segments, this readings have been taken, and saturated water content at x is equal to 0 is theta is equal to 0.39. So we need to calculate and plot the Boltzmann transformation function lambda theta and hydraulic diffusivity function d theta for the soil, right? Okay. So in this problem, we need to make use of few formulas. The first one is of lambda. The lambda is defined as lambda theta is equal to x upon square root of t. Square root of t is the time, and time in which we are taking the measurement. Okay, so here it is given at 1500 minutes. And then, if for first calculation I show, then lambda will be equal to x upon under root of t. X is 76 divided by the square root of 1500. Right. So if we determine that's going to be 76 divided by square root of 1500, so that's going to be 1.962 as given here. Okay. And in this way, we can calculate all the lambda values. Mm. And secondly, we need to determine the cumulative increment in area. Okay. So for that, we first need to determine the area at a particular lambda and theta values. So the area increment in the area AI, which is given here with this formula, is written as theta I minus 1. And then the multiplication of lambda I plus lambda I minus 1 divided by 2. So the average of lambda I increment and lambda I, right? So in this way, we can calculate this AI value here. And based on this, we will be calculating the cumulative increment, that is the summation of the AI plus A till AI plus 1, and then the increment at a particular ith iteration, right? Then we need to determine the increment of the slope, that is d, which is given here, d theta upon d lambda. So to determine d theta upon d lambda, we will use this formulation, that is given at theta I minus 1 upon lambda I minus 1. And then the diffusivity function, as we know, is going to be zero point 0.5 times d lambda upon d theta, or it is equal to 1 upon si. It will be the same. And then the integration of here it is given integration. Here you can write the summation of the area, this area under the curve, right? And so we'll solve this equation on Excel sheet so that we can solve for all the values. So let me just take a screenshot of all the formulas which we are going to use, right? And then we'll switch to an Excel sheet here. So I'll be copying these terms here for better understanding. So in the question, we have been provided with two values that are for the x value and the theta I value, right? And we need to calculate the values of first the lambda I for each iteration, then the value of the AI, then the cumulative of AI, then the SI, that is actually the inverse of the slope, and then the diffusivity. Fine. So here, the time given for the calculation of the results of the analysis is 1500 minutes. Okay, so we'll do all the calculations in centimeter and minutes. So first we'll calculate the lambda I. Lambda I is given as x upon under root of time. So it will be equal to the x value that is given in A2. That will be divided by the square root of the time, that is 1500 seconds, right? and time will remain constant for all the values. So we'll allow this value. Okay. So we have obtained a lambda I value of 1.9623. If we copy it, then we'll obtain the value of lambda I for each increment in x value or the each distance. Right. To calculate the cumulative area, what we'll do for the first one, we'll leave it blank. For the second one, it will be based on this formula. So the that the AI is actually equal to theta I minus theta I minus 1, and then it will be multiplied by this lambda I plus lambda I minus 1 divided by 2, right? So first we will see what is the value of this theta I, that is 0.04, and subtract by the point theta I minus 1, that's 0.02. We'll multiply it with 0.5, that's 1 by 2. Then we'll further multiply it with lambda I plus 1. So lambda I is C3 plus lambda I minus 1 is C2. Okay. We hit enter and we'll get the value of AI for this particular increment or the particular incremental value. Then if we copy this formula overall, then we'll get the value of AI for each increment. Right. Now we need to calculate the cumulative values of this area and this curve. Okay. So for that we will write the formula that the cumulative value is actually equal to the previous value. For this one, it will be the same as this one, and for the second value, it will be equal to the cumulative value in the last step plus the value obtained in this step. So if we copy, we'll get all the cumulative values in which the areas are like added up as we go far from the initial point of the left hand. Okay. Then we calculate the value of SI. SI is nothing but the inverse of the slope. So that will be equal to theta I minus theta I minus 1 upon lambda I minus 1. So if we write it here, that's going to be theta I minus theta I minus 1. And if we divide it by lambda I minus lambda I minus 1. So the slope of the SI, the slope will be negative as we know, and we will obtain the values of SI for all the equations, all the values. Fine. So till this point, I think should be clear. And um, now we can go further and calculate the value of diffusivity. To calculate the value of diffusivity, we will use this formula that states d theta is equal to minus zero point 0.5, 1 upon the slope, and the summation of the area below the curve or the below the values. As these are discrete value, we have used the summation. Okay. So we'll write the formula here. That's going to be minus zero point 0.5, and we'll multiply it with the summation of the area, cumulative area, and we'll divide it with the value of the slope SI. And with this, we can obtain the value of the diffusivity for all the value of x and theta I, right? So you can try it till here and let me know if there are any issues with this one. So if we move further, then we needed to calculate and plot the Boltzmann transformation function, that is lambda, and the hydraulic diffusivity function d theta of the soil. So how these values are changing over, then we can plot, we can make two plots. First one is the theta versus lambda plot, the theta versus lambda plot, and the second one we can make the diffusivity versus theta plot. So here we'll make two plots. The first one is theta versus lambda. So let's see how it looks, and we plot like that. So now we need to change the data here. We could edit the x direction. We'll need the values of lambda, and in the y direction we need the values of theta. Right. This graph will look something like this. Okay, and we'll add the title. Okay. So in the x-axis we have the lambda, right? And in the y-axis we have the theta. So here we can see that as the lambda value is increasing, theta value is decreasing, and it drastically decreases after a certain lambda value, right? So now if we make another plot, that's going to be the diffusivity versus the theta value. So we'll select these two and we'll insert a plot. And this plot will look something like this. And we can select the data again. So we'll put edit. The x value is going to be theta I, and the y value is going to be diffusivity. That's fine. Okay. So hit OK. And we'll also add that this title here. Theta. And here this is diffusivity. Fine. So if we see here, then as the theta value is increasing, or the volumetric water content is increasing, the value of the diffusivity is also increasing. Initially, it was usually constant. At the end, it increases drastically, right? So these are the two variations which we needed to plot. Okay, these are the formulation which we have used. You people can try making these plots, and you can also try it with the different combination of data. So these are the two plots which we have plotted, and this one looks little hazy here, but it's actually going to be like this as we have plotted. So while we discussed on the transient flow, we were solving the problems of the flow of water, the transient flow of water from the pores. And there can be the flow of the water vapor also, okay, and the air also. So air diffusion, vapor diffusion are two different, two separate problems. Okay, for that also the Flix law is provided, and we can study the air diffusivity using this formula. Okay, that is minus d, the diffusivity, and this is mole per meter cube, the vapor density. Okay. So from the transient flow conditions, we are moving on to the shear strength condition. Moving on to the shear strength condition. So in the shear strength problem, we usually do the direct shear test. Okay, we call it simple shear test. In this problem, we apply some normal load, and the sample is sheared, the soil sample which is placed in a predefined plane, right? So this behavior is for the saturated soil. And saturated soil, we use the Morpholm equations, that is tau is equal to sigma tan phi plus C. Okay, and we usually obtain this kind of behavior where shear, if we plot shear stress versus the horizontal deformation, then we'll obtain this For the loose sandy soil, we'll obtain this behavior, that is the strain hardening behavior. And for the over-consolidated soil or the densely sand compacted soil, we obtain a peak here. So after reaching peak, the sample will reach to a critical state. So that is called the stream softening behavior mostly. And if you plot the observation from multiple tests here, then we'll obtain this line from where we can determine the value of cohesion and the friction angle. Okay, so this is defined as tau is equal to sigma tan phi dash, or in the total stroke sigma tan phi plus g, right? So it's the equation of a straight line. Then, based on these static shear apparatus, we can solve one numerical problem. And this problem says that the shear box test results from two samples of the same soil, but with different initial unit weights as shown in the table below. The sample A did not show a peak value. As we can see here, the vertical force is always increasing to 50, and the horizontal force is like increasing only 150, 269, 433. And in the second sample, it says that the sample B shows the peak behavior. Okay, and so how we can do that is first we need to plot these values on a plot so that we can see that what type of peak behavior it is showing, right? And then we will need to calculate the phi critical state, the phi peak at 204 Newton, and the delta tension angle, right? So if we plot it here, then let's see if I can zoom this one. Hmm. So okay, so here if you see, we have been plotting it on different scale. So if for the first test, we'll plot the vertical force is 250. So corresponding to 250, we'll plot this point, right? And here we'll write corresponding this point, okay? And corresponding to 500, we'll write 269, and corresponding to 750, we'll have 433. So this straight line is obtained. Okay, and the because the first sample is showing the real state behavior, or it is not showing a peak behavior, so the angle obtained from the soil one will be the critical state friction angle. So that will be pi dash CS. Okay, so this angle if we obtain, we can take n2 values, or we can best fit the line between these three observations, and we can obtain the friction angle by setting C as 0. Okay. So the values of the so value of the C will be 0, and if we obtain the slope, then it's going to be around 32 degrees. So the phi dash critical state is obtained as 32 degrees. And when we move further, we can obtain the value of phi dash P at two stress conditions as asked in the question. The first one is first one is for the 200 Newton vertical force, and the second one is for the 400 Newton vertical. So corresponding to 200 Newton vertical force, we have a horizontal force of 175. Okay, so we'll determine the angle as tan inverse 175 upon 200. Okay, tan inverse horizontal force upon vertical force. So we'll obtain a value of 41.2 degrees. So if we do tan inverse 175 upon 200, then it's going to be 41.185. That is equal to 41.2 degrees. And if we do it similarly for the 400 Newton, then we will obtain The value is at tan inverse 248 divided by 400. So tan inverse 248 divided by 400 for test 4. So 248 and 400, it will give you tan inverse 248 upon 400. That's going to give you 31.8 degrees, right? So we have determined five critical states. That is uh, I think not 32 degrees, but the 30 degrees answer. Okay. I missed it here. So five critical state is 30 degrees and five peak at two particular stresses you have obtained here. So based on this, you can determine the value of dilation angle. Okay. Sample which shows the peak behavior it can be determined. The dilation angle can also be determined for them. So at 200 Newton, if we determine the dilation angle, that's going to be 5p minus 5 critical state. So 41.2 minus 30, that's going to be 11.2 degrees. And for the 200 Newton, we'll have 31.8 minus 30 degrees. So that will be 1.8 degrees, right? So we have determined the critical state angle of friction, then we determine the peak angle of friction and the dilation angle. Okay. So take your time in this question. Let me know if there are any doubts. So we have studied about the simple direct shear test, mostly for the saturated soil samples. Okay, and to simulate the behavior of to simulate the this shear strength of the unsaturated in the unsaturated condition, we use the modified direct shear test. Okay, or in the Praxel test also we usually do that. Okay, so in the modified direct shear test, as we'll see here, we we basically apply air pressure and we maintain this air pressure and the water pressure using back pressure using this back pressure concept, and then we can maintain UA minus UW. Okay, and as we have the control over the UA minus UW as we were having in the case of the axis transformation technique. So in this controlled chamber, we can have the control over UM and SUW, and we can change this vertical stress sigma. So, based on this, we can determine the values of the horizontal strain, horizontal stress, horizontal strains. Okay. So the same texture test can be performed in the controlled environment for the different suction levels. Human is suitably suction. And the similar concept is valid for the tri-excel test. And here, the thing to note here is that as we know the Bishop's equation, that's actually the sigma dash is equal to sigma minus UW, right? For the partially saturated soil, it's converted to sigma dash equal to sigma minus UA plus this effective stress parameter multiplied by U minus UW. Okay. This effective stress parameter represents that how much amount of this matrix suction U minus UW is giving an effect on the effective stress values sigma dash, right? So if we consider this x zeta value as 0, the effective stress parameter value as 0, then sigma dash will be equal to sigma. Okay. And if we also consider the UA as 0, and for a zeta value as 1, we'll have sigma dash equal to sigma minus UW. That is for saturated soil, right? So these are the two extreme cases of this partial saturated soil, the dry and the wet cases. So the for this kind of apparatus where we are controlling the matrix suction value by controlling the pore air pressure and the pore water pressure, we will be using this equation to determine the effective stress. So sigma dash will be equal to sigma minus UA plus this effective stress parameter zeta times UA minus UW. And based on this, if we calculate the shear stress tau, that's going to be sigma dash tan phi plus C. And putting the value of sigma dash, we obtain this expression, right? So this expression is going to be very useful for determining the values of phi dash, C dash, and this effective stress parameter for the passive saturated soil or the test which are performed on the passive saturated or unsaturated soil. Okay. Then here, if we see that in the case when the zeta value is equal to 0, this will be changed to the same as the Coulomb's equation, C dash plus sigma tan phi dash. If UA also we consider zero. In the Dirac test, we have studied that in their results, the control Dirac test, the result shows a trend that if we see that if the suction values are very low, then this soil will behave in a elastic strain hardening manner. Okay, so it will reach to a critical state, right? But as the suction value will increase further, these soils will show the strain softening behavior. Okay, they will reach a peak, then they will come back to critical state, right? And it is also a good observation to see here that if we plot tau versus sigma minus UA value, then we will see for all the matrix suction values, this slope is almost constant. So that slope actually is represent the this effective friction angle. So it is a constant. Then so we can think that we can say that for all the values of matrix suction, this pi dash value and the C values are not changing, right? This we have studied in the theoretical class that, as in the case of the loose files, because of their packing as a simple cubicle, and when we apply a shearing stress, their packing changes to tetrahedral. Because of this, there is a strain that takes place. Okay, and because of that, they show this kind of behavior. Okay, the positive strain is observed. But in the case of the densely dense soils, densely compacted soils, in that case, these particles are already in the tetrahedral state. So when horizontal stress is applied, these will particles roll up, because of which volume will increase. So in the starting, they will show a dilation behavior. Okay, and if we see here for the case of the matrix section also, at lower matrix section, the behavior will be just like that. Okay, so these will not show any dilation, but at the matrix section values will increase, they will start showing this kind of behavior. Okay, this may be considered, this may be understood using the same, thinking about the same concept, but just that the water is there, which is having the tension, surface tension, or the suction values. So, based on this concept of matrix suction, the modified effective stress principle is given. So, the Bishop's equation is modified, and it can be used in the format that sigma dash is equal to sigma minus UA plus zeta times UA minus UW. And this zeta is effective stress parameter. And if we uh, reorganize these terms, then we'll obtain that at the failure, if we write this equation of the shear stress at the failure, then we can obtain the value of zeta f at failure will be equal to tau f minus c dash and sigma minus ua. So all these terms we are sending this side, tan phi dash upon u minus uw tan phi dash. So this equation will be very useful to calculate the value of this effective stress parameter from the laboratory test. So let's say we'll solve this one example on the sandy soils, and the suction control direct shear test was performed on sandy soil, and the observations are provided in this table. So the first observation says when the value of U minus UW is zero, or the matrix suction is zero, at that point the value of sigma minus UA is 200, and value of failure value of shearing stress is 150. So how we can calculate the value of this effective stress parameter at this point? So we'll see here, as no matrix section is working, that means u minus uw is 0. Okay, so this term is 0. So this term will be multiplied by 0. So at this case, we also know that the effective stress parameter can vary from 0 to 1. Okay, so if we put the value of UA as 0 here, then we'll obtain that the XF will come as an infinity. But we know that the value of XF is limited to 1. So we will take the value of XF as 1 here. 1 is like very high value. Okay, so that's mostly in the case of saturation. And we can write the value of XF here as 1. So the first observation which you see here, that actually can be used to determine the value of C and phi, C or phi. But here, as the soil is sandy, so the value of C is 0. Okay. Then if we use the concept of Mohr, that is tau is equal to C plus sigma and phi dash. Okay. And in that case, like this equation, C plus sigma dash tan phi dash. Sigma dash will be sigma minus UW. Okay. And if we rearrange, then phi dash will be equal to tan inverse of these values. Okay. And the tan inverse of tau f, the tau f value is given here as 150. Okay. And the value of sigma minus UA or UW is given as 200. So that will be equal to tan inverse 150 upon 200. That will give 36.86 or 36.9 degrees. Fine. So from first observation, we can determine the value of phi, and we are assuming that this phi will not change as the matrix section is changing. So Pi will remain same for all the time for the same material, right? So we will now make use of this equation which we studied here that came from the modified Bishop's equation, and using this we will determine the value of this matrix suction, this effective stress parameter for different suction levels. Okay, so we'll be doing this one by hand calculation, and others we'll do in Excel. Okay. So we can see here the value of x can be written as tau f minus c minus sigma minus ua 10 pi dash upon ua minus uw at failure 10 pi dash. The value of the tau f at let's say for the second reading is 105, and minus c dash is 0 as it is a sandy soil, and sigma minus ua for this is 120, and the tan inverse and tan of pi value we have determined 36.9 degrees. At the bottom denominator, we will write the value of u minus uw as 20 tan 36.9 degrees. Now let's calculate it. That's going to be 105 minus 120 multiply tan 39.36.9 divides 20 multiply tan 36.9. It will be equal to 0.9923. So the value of this effective stress parameter for the first 20 section 20 debut section is 0.9923. Now let's solve it for all other section values in Excel sheet. So let's jump here and make a new spreadsheet. We will copy these values. So let's copy these values here. So we'll write test number here. Then we will write this UA minus UW in KPA. Then the second term will be equal to sigma minus UA. It's going to be, let's say, sigma minus UA. That's also in KPA. The third term is going to be tau, or here stress. That's also in KPA. And the last value we are determining the effective stress parameter, effective stress parameter. So for the first test, second test, third test, fourth and fifth and sixth. For the first one, the value of matrix action is 0, 20, 50, 200, 500, and 800. Sigma minus UA is going to be 200. Give me a second. 200 and 120, and then 120 constant at 120 for all other tests. Then we'll have the shear stress value of 105 and 172 and 240 and 210 and 205. For the first one, we have determined the vector stress parameter as 1. For the second one, let's calculate it. So what was the formula here? Let's write the formula. That's going to be, let's take the formula from here only. So the formula is the effective stress parameter will be equal to the value of the Numerator, the value of tau f at failure minus theta s is equal to 0. So let's write 0 minus sigma minus ua. So sigma minus ua is going to be this value. It will be multiplied with tan of the number that is phi dash. Let's say we determine phi dash and we'll write it here. And we'll log this value and then we'll close the numerator in the denominator. We'll write the value of u minus uw, it will be 20, and it will be multiplied by again tan of phi. Log this value and close. So we need to define the value of phi here, what we have calculated. So in the question, if you see, we have calculated the value of phi as 36.9 degrees. So we'll write here phi value as 36.9 degrees. There might be some error. Let me check. Okay, so these values it is taking in radians. We need to convert it into degrees. Okay, so to convert it into degrees, we multiply 180 upon pi. Similarly, here also we multiply it by 180 upon pi. Right? Still there's some problem. Let me cross check. Okay, so I think I've done it opposite. We will multiply it pi upon 180. And this one also will multiply by pi upon 180. So now it is giving 0.9923. Okay. And as we know, the value of psi varies from 0 to 1. So here we can obtain the distribution of the vector stress parameter with XF at different level of suction values. Okay. So, if you want to try this one, please do that. And let me know if there are any problems. Meanwhile, we'll take a break of 10 minutes so that we can continue further. In this question, we have solved for to determine the value of effective stress parameter. And based on the values of matrix function, this effective stress parameter changes as the matrix function increases. The effective stress parameter keeps on decreasing. So, if we see here, as the matrix function will increase, the volumetric water content, or if we plot normalized volumetric water content, will decrease. This effective stress parameter will also decrease as the matrix function increases. And we can also plot this effective stress parameter against the normalized water content, and then we'll obtain the curve that it will depend on certain values. So if we see here, and the exception provided by Lu and Lucas, and it says the value of effective stress parameter. Actually, they have provided some empirical equations. The first one is that effective stress parameter is equal to psi m, okay, metric section corresponding to the metric section which is there, and the metric section corresponding to the air entry value, and to the power minus 0.55. This expression is valid. This is a discontinuous expression. The first expression is valid when metric section is greater than the air entry value. Okay, and so if we see the plot here, then it will look something like this. So if the matrix section is greater than, this is psi e, let's say, if the matrix section is greater than this value, then this expression is valid. And if the matrix section is lesser than this value, then the psi has become 1. Okay, because here the soil is mostly saturated only. Theta S. Okay, and right. So as we see here, this is mostly saturated, so psi f is 1. So this is actually for the drying cycle. Okay, and then the second expression is also provided that denote that this effective stress parameter will be equal to theta upon theta f, the theta which is there, and the degree of saturation volumetric water content at saturation 1, or at saturation, to the power k. K is a factor. Okay, as the value of k increases, this will keep on taking a curve path. Okay, and this normalized water content we have already seen, theta minus theta r upon theta minus theta r, right? So we will here we will solve this one more example that will be on the same Dijkstra test, in which the matrix system is controlled, or so the controlled Dijkstra test. And the question says that a series of direct shear and soil water characteristic test was conducted for an unsaturated clay sand mixture, unsaturated clay and sand mixture. Results are tabulated in table 6.2. Determine the shear strength parameters C dash, phi dash, and determine the functional relationship between effective stress parameter, this effective stress parameter, and the degree of saturation S. Then we need to plot matrix suction and effective stress parameter as a function of saturation. Okay. So what we have here is we have a number of tests. Then we have the matrix suction values for each test. Then we also have the readings of the degree of saturation. Then we have this value of sigma minus UL. Okay, and the value of tau. Then we need to calculate the value of this effective stress parameter first, and then we before that we will have to calculate the value of this phi dash and c dash, right? So we'll do it for the first two reading. If we'll see, the matrix section is 0. So, and the degree of saturation is 1. So these two readings will give you the values of C and phi, because in these two It says we can use the Coulomb's equation, that is equal to tau F is equal to C dash plus sigma dash, or you can write sigma minus UA and phi dash. Okay. So if we take the first value, then we can write tau, that is 292, will be equal to C dash. C dash is unknown, plus sigma minus UA is 300, 300 and 10 phi dash. This is one of the equations, and the second equation will be 141 will be equal to C dash plus the value of sigma minus UA is 120, tan phi dash. So now we will need to solve it. For solving it, we can just subtract these two equations and then we'll obtain the value of phi dash. So the value of phi dash will be equal to 292 minus 141, then divided by 300 minus 120, C and C will cancel. Then we'll have to take tan inverse of this answer. So it will give you the value of phi dash as around 40 degrees. Okay, and you put this value is any of these two equations, and we'll obtain the value of C. So let's say we put in the second equation, then we'll obtain C dash is equal to 141 minus 120 multiplied tan 40 degrees. So it gives you the value of C dash as 39.3. So here also we can write as 40 degrees. Okay. So C dash we obtain 40 kPa, phi dash we obtain 40 degrees. This is 40 kPa. Okay. So from the first two set of data, we have obtained the value of C dash and phi, C dash and phi dash, right? So now in this equation, the modified Mohr-Coulomb's equation, modified Bishop's equation, we have this value of C dash known, sigma A minus UN known, UA minus UW known, and 10 phi dash known. So now we just need to calculate the value of the stress parameter XL, and we have the value of tau F also known. So for each observation, we will calculate the value of this effective stress parameter. Okay, so let's take help of Excel again, and we'll do that. So first, let's take the screenshot of the value which are given here, and switch to Excel. Okay, make a new sheet and we write these values here. So first is test number. The second one will be UA minus UW. The unit will be KPA. The third one is going to be degree of saturation. Yes. After that, it will be sigma minus UA. That's going to be in KPA. Moving further, we'll write this as shear stress in KPA. Moving further, here we need to calculate the effective stress parameter. Okay. So the first one is test number 1, 2, and we are going till test number 10, right? And the value of UA minus UW will write. For the first one, it's going to be 0, 0, 25, 500, 1000, 2000, 5000, 11,000, and 15,000, then 50,000. So a high value of matrix system values, we are high range of matrix system values we are covering. Degree of saturation is 1 for first two, then it's going to be 0.98, 0.78, 0.71, 0.64, 0.45, 0.38, 0.35, 0.2. 0.38, 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, 0.2. 0.35, and the value of sigma minus UA is going to be 300 and then 120 for all of them. Value of shear strength is going to be 292, 141, 160, then 300, 400, 460, 500, 590, 530, 525. Okay. So the next thing is that we need to calculate the effective stress parameter. So for the first two cases, these are for the saturated cases. So effective stress parameter will take its maximum value as 1. Then as we move further, we'll calculate the effective stress parameter based on the formula which we have seen there. And what was the formula? If we just print screen this one and we type it here. So in this formula, before that we will what we have calculated the C dash and the pi dash will write here. So both were approximately 40 we have taken. C dash is in kPa. Okay. So to calculate the value of vector stress parameter for other matrix section values, we will use this formula. So this formula states that theta psi f is equal to, in the numerator we have tau f, shear stress, minus C dash, that's given here, F4. In the last numerator we had this C dash value as 0, minus sigma minus UA, that's here, multiply tan of phi dash. So in the denominator we have UA minus UW, UA minus UW, multiply tan of phi dash. Okay. So here again we need to change all the this degrees to in this degrees to radian. We'll multiply by pi by 180, and here also we'll multiply by pi upon 180. So we'll get the values of the effective stress parameters here. Fine. So we use this two values to determine the C dash and pi dash. Then we use the value, the formulation to determine the value of effective stress parameter. Now we move back to the question. It says that determine the functional relationship between the effective stress parameter psi and the degree of saturation S. Okay. So determine this we have to plot. Then we have to plot matrix suction and effective stress parameters as a function of saturation. Okay, so there are multiple plots which we can do here. The first one is that we'll plot between the degree of saturation and effective stress parameter. So if you plot that, the degree of saturation and the effective stress parameter, so we'll insert plot and this plot. Then we will format this like that. So this one is for the effective stress parameter, and the x-axis, the y-axis I want to be the effective stress parameter is going to be psi, effective stress parameter, and the x-axis I want to be degree of saturation. Let's check the data, add it. The x-axis is degree of saturation and the y-axis is effective stress parameter. So as we see, the degree of saturation is increasing, the effective stress parameter is increasing. Fine. And as it reaches the value, there are two values which are plotted here. That means at the degree of saturation of 1, the effective stress parameter is also 1. Then for then we need to make some other plots also. Those are between the, let's read it again. Those are between the plot matrix section and the effective stress parameters as a function of parameter as a function of saturation. So the similar plot which we have plotted for effective stress parameter, we can plot for the matrix section also. So let's copy this plot here and we try to make another plot where this effective stress parameter will be changed with the value of matrix section and it will be APA. Okay. So for that, if we see here, we will change the data. So the edit, the series name will be UMMFUB and matrix section, and the x-axis will be the degree of saturation. The y-axis will be the matrix section values. And we need to confirm, press OK. Okay, here this. So as we see, the degree of saturation, we can scale it. Um, and, we need not to go much longer. Access options, we just need to take from 0, right? 0 to 50,000 is enough. So here we'll see as the degree of saturation is increasing, the matrix section values are decreasing. So it is natural that as the more water is coming into the soil matrix, the matrix section value decreases. Okay? We can also similarly plot the value of shear stress with the degree of saturation and can also plot other values also and from the consideration between effective stress parameter and degree of saturation as okay. So to determine the functional relationship between the this effective stress parameter and the degree of saturation F, what we'll do is that in this plot where we have plotted all the values, we'll fit a curve maybe. Okay, so let's do some curve fitting. Okay, at trend line. So if we fit a polynomial of order 2, then you'll see it is fitting very well, right? We also want to see the equation on the chart. So it's going to be like that. And as per value also. And let's say I want to this polynomial of order 1. Okay, so like this way, you can fit different type of curves here, and based on the best fit which we have obtained, or based on the value of r square, we can say that which polynomial is going to be the best fit, right? And let's see here that we have determined everything, and here in the question, if we look for this expression which we have studied, that is going to be the effective stress parameter and theta upon theta s. That's mostly we can write degree of saturation also. It's equivalent. So if we come here and we try to fit a curve, we try to fit a curve here that will provide you the relationship like that only. That effective stress parameter is equal to, let's say, effective stress parameter, let's say predicted. It's equal to some, it's equal to some s to the power k type. Okay. So here we can, if we take k value as 3.5 and we write it here as it is equal to s to the power k times, then it will look something like this. And I think we need to fix the k as 4. Okay, like this. So if I also plot these values along with the values which we have plotted, then we'll go to select data. We'll add a new series. The name will be the predicted values. The x values will be equal to this degree of saturation, and the y values will be equal to whatever the values which we have predicted. Click OK. Okay. So here you see these are showing a very good match, right? These are showing a very good match. So if now I change the value of k to 4, this curve will increase. For 5, it's going further downwards. For 2, it's far up. For let's say 3.3. So we can obtain at what value this will obtain a better fit. Okay, that we can also do using some expression using the solver program. So for the solver programs, if I do it, we'll insert a column here, and here we'll obtain what is the error is there. Okay, and maybe mean square error or the squared error. So that will be equal to predicted value minus the value which we have obtained from the Bishop's equation and the square. And here we can take the summation, sum of these squares. Okay, this is sum. So we can now optimize this k value to minimize this one, right? So let's take the solver program and okay, so select objective. We need to minimize it to choose objective. Choose objective. This one is our objective. Okay, there are some problems here. That's going to be H and 12, right? And we need to minimize this H12 and input cell, which input cell I want to change. I want to change this cell. I want to change this K4. So I'll write K4 and I'll click OK. And that will be all. Constraint, model type, zones, and let's see what we get. Okay, let's close this one. We'll use make use of this solver which we have here. So in this solver, we'll select the values of the objective function, which is this one. We need to minimize this by changing the variable k4 and everything else. Okay. in a value of 3.607. Key solver, that's going to be okay. Key solver solution. So for a value of k 3.6, we obtain the best fit here. Right? So in this way, we can solve this kind of problem. And with this, we come to about assignment equation. The first one is that the parameter that effect stress parameter is to represent the state of stress in unsaturated soil. So if we see here, the state of stress in unsaturated soil is represented by sigma minus um minus uw. That how much suction is there, and the x value is usually the ratio. Okay. So this ratio actually represents the state of the stress, right? Even from this equation, we can see that this x value will represent what the state of the stress is there. Okay. Because it is mm, a function of degree of saturation of the soil mass and reflects the contribution of matrix section to effective stress. Now the second question says the Boltzmann transformation provides solution to the theta form of the recharge equation for transient flow through sites. So this is correct. The Boltzmann equation provides the solution for the theta form of the recharge equation for transient flow of soil. And then we have the variation of diffusivity coefficient with volumetric water content d theta in a soil column can be estimated from the measured theta xt value. So if we see here, if we measure theta xt value from the experiment, okay, and the variation of theta with the x and t, then we can plot this graph, and from this plot we can obtain the slope. And we have also done a numerical on the same, and we already have the value of lambda, so we can find this area, and then based on this formula, we can obtain the value of d theta. Okay. Then it is said the rate of vapor pressure, vapor flow, so soil is independent of the variation in the vapor, water vapor density. So uh, if we see the Fick's law for vapor flow, then we'll see that the flow of vapor to the soil is dependent on the this dV, that is the diffusivity coefficient, and this delta of PV, this PV. Okay. So the PV is this rho V is actually the vapor density, or the absolute relative humidity of the pore water vapor. So the this flow actually depends on the this vapor density, water vapor density. The rate of independent may not be a correct statement. Then we have a question that says in the suction control shear test and on unsaturated soil, as the suction increases, the strain behavior of soil always show strain hardening response. So as we have studied in the theoretical class, as the suction value is increasing from 0 to 10 to 50 and so on, this curve initially will show a strain hardening behavior. But as the suction value will increase further to higher values, 200, 400, etc., in those cases, these will show a strain softening behavior, just like a over-consolidated soils or the densely compact soil. Right. So this statement that in the suction control shear test on unsaturated soil, as the suction increases, the stress strain behavior of the soil always shows strain hardening response may not be truly correct. Right. So these things which we were given in the assignment, which we can answer based on your knowledge, and that's all I have for today. And now I'll ask the people if you have any doubts, please do ask. And, I'll wait here for some time so that people can regain what I've taught and ask the question. Okay, so as there are no questions, I think we can close this lecture for today, and we'll meet again in the next lecture. Okay, so thank you everyone for your time. Thank you.